Thank you first for the organizers for organizing this really amazing program. I've had a really fantastic 3 weeks of stay already. So today I'll be talking about our recent results on quantum reservoir engineering. This is a direct segue from the previous talks where the idea of using dissipation as a resource for reinforcing coherences in large quantum systems. What my focus would be is how to do that and what is how the range of dissipation. You have already heard about short and long range interactions, but how about the range of dissipative interactions can actually manifest in your quantum states, and specifically from the point of view of entanglement stabilization. So without further ado, let me first give you a very broad overview of what is the paradigm of quantum reservoir engineering. The idea is very simple actually, that we all know that, that quantum systems are never really isolated. They are always talking to some uncontrolled degrees of freedom, which are uncontrolled either by design or by circumstance. And the idea of Hamiltonian engineering, which has been the prevalent view of quantum information processing, has to be to make these quantum systems as pristine as possible, as coherent as possible, and or use some kind of clever pulse engineering like dynamical decoupling to actually suppress the errors which are induced on the dynamics of these quantum systems because of these interactions which are uncontrolled. So the quantum reservoir engineering kind of turns the tables on this picture. It says actually maybe unlike uncontrolled dissipation, which I'm saying like basically showing that this large big bubble with some reservoir of degrees of freedom which you don't have no control over. But maybe if we actually introduce some auxiliary quantum systems which are purposefully actually made to interact with your desired target system strongly, then maybe can actually help reinforce decoherences. And the typical way of thinking about how much it is helping is to see that can you actually stabilize, let's say, a non-thermal state. We know typically open systems thermalize. Can we actually stabilize the system in non-thermal states? And more importantly, can these non-thermal states even be like maximally entangled resource states, so that these states can persist and be available on demand? So in the theory speak, we basically write a master equation. This is a very typical simplified master equation, and if you're interested, I'll be happy to comment on why we want these. So this is actually very easy to understand why I want this coupling to be strong, because in the theory speak, when I trace out all the degrees of freedom which I don't care about, my quantum system will be described by having a good rate of dissipation, which I'm calling capital gamma, and a bad rate of dissipation, which is small gamma, which is not in my hands. And if this engineered dissipation rate actually overwhelms the uncontrolled dissipation rate, this is the so-called reservoir engineering regime. So that is the reason that this interaction has to be much stronger than the other interactions of the system. And the particular interaction which I'm showing as weak, this is actually a technical point which is also interesting. This is because we actually do not want any kind of non-Markovian effects typically coming from the auxiliary system, at least because these kind of time-dependent effects are even more hard to control. And this particular paradigm of reservoir engineering with some variations has been around for almost more than a decade. It was first introduced by Sirac and co-workers, where the idea was to actually do the entire computation dissipatively, not just state preparation. The reason for that is that these kind of prepared states or quantum operations are necessarily stable and robust to any kind of spam errors, which is basically state preparation or measurement errors. Plus, there is no heralding or post-selection involved. So unlike measurement-based protocols, there is no qubit overhead. Because of that, there have been quite a few experimental demonstrations of these ideas. But let's take a step back and see, again, maybe this audience is already super informed, but for the people who do not work on quantum reservoir engineering, what are the kind of conditions one has to satisfy so that you actually have a non-thermal quantum state appear as a steady state of a driven dissipative dynamics? So I'm taking a very simple example. Let's say that I have a 2-qubit target system and I want to stabilize it into a maximally entangled Bell state. Okay? So this is my target state psi, and then there is some other states in my Hilbert space. And basically, I want to say that if I'm actually, this is the dark state of my dynamics, this is again an AMO language which we have borrowed, then it should be the eigenstate of my Hamiltonian physics and a dark state of my jump operator, or the null state of my jump operator. So that is the idea of, it's very obvious why we would want that. But there's another condition, which means that I also don't want to just stay there if I'm in state sky. I actually want to prepare it. So it means that irrespective of where I start in my Hilbert space, there should be at least a feeding link into my target state, which essentially means that my target state or subspace should belong to the right null space of the jump operator, but not to the left one. So both these conditions have to be simultaneously satisfied if I actually want to stabilize any kind of subspace of pure states. So there is a very interesting caveat for linear dissipation, and obviously for several reasons one would like to start with linear dissipation. Linear dissipation just means that your jump operator is typically a linear superposition of several like one excitation jump operators or de-excitation ones. Experimentalists love these kind of dissipation channels because they're very easy to implement using simple sideband pumping and so on and so forth. And very soon you realize that actually you run into this kind of a no-go theorem. If you try to write down these two conditions for a simple Bell state, you see that your engineered jump operator actually turns out to be a superposition of total spin operators, cis spin up and total spin down operators, which essentially means that by definition your jump operator commutes with the total spin. And your Hamiltonian necessarily, since it's an eigenstate, it has to be the total spin also has to commute with the Hamiltonian. So basically what it means is that actually with linear dissipation, the total spin remains conserved under the full Liouvillean dynamics, which essentially means that you will, instead of actually having a well-connected Hilbert space, which goes into one unique target state, we will actually have disjointed subspaces because of too many symmetries in the system. So with linear dissipation, it's actually impossible to satisfy both these conditions simultaneously. So people actually realized this problem early on, and the point was to actually take a perturbative approach to quantum state stabilization. That, okay, it seems that it's actually hard to stabilize exact entangled states. What if we actually stabilize something which is almost entangled? So for example, this is a common, very commonly used trick, and in fact all the experimental demonstrations I talked about actually use this trick, that you actually take some kind of a coherent superposition or admixture of your target desired entangled state with some other state, in this case the joint ground state, using some kind of a symmetry breaking term. Because the whole problem is there are too many symmetries in the system, which leads to these kind of disjoint subspaces. So what if we actually break the symmetry, and that way we can actually get a channel to get into this target subspace through the phi 0 state. Phi 0 state is something which you have to introduce, which in this case happens to be the joint ground state. And it works very well, but the problem is that because the entire theme of symmetry breaking is to basically introduce an admixture with a small error delta, if you actually try to pump this state hard, which means you try to do the stabilization with a fast rate, you also increase the error in your target state. So which essentially means that the time it takes to stabilize an entangled state and that error in that entangled state are actually correlated, sorry, anti-correlated. So it means either you can do a very high fidelity stabilization where it takes very long, or you can do a very fast stabilization where the stabilization fidelity is very, very low. So in that sense, this is the problem of all quantum reservoir engineering protocols, which I'm hopefully going to show that it's actually not a fundamental bottleneck in the coming slides, that there's always an intrinsic error in these protocols, which is actually determined by the protocol itself, like for example, the delta. And this typically scales with the rate of the stabilization. So which essentially means it's anti-correlated with the time it takes, which is the inverse of this gamma. And then there's always an extrinsic error, which is the whole point of having the reservoir engineering in the first place, which is determined by your hardware or the decoherence. And to 0th order, there's an extrinsic error, which is just the hardware dependent error, is kind of independent of your protocol. And if you just take a very simple model of what is your total fidelity, which you just multiply the fidelities, which is the intrinsic times the extrinsic fidelity, you actually see that your total error is not just the sum of these two errors. There's this cross term, so it's kind of boils down to kind of minimizing the area of a shape with a fixed perimeter, and that we know that that is a square, for example, if there is a two-dimensional figure. So that essentially leads to an optimality that it doesn't actually make sense to ever optimize anything below the intrinsic error, because the best you can do is to make all the error channels equal. So that is what sets the kind of the minimum error of all these reservoir engineering schemes. So when we started working on this problem, our aim was to actually do an exact entanglement stabilization, not a perturbative entanglement stabilization, which essentially boils down to the fact that we have to design protocols which do not have any intrinsic error. The only error channel should be coming from the hardware or the decoherence. So the minimal instance, actually, since I already showed you that with linear dissipation, 2 qubits stabilization or entanglement is a no-go, the minimal instance we tried out was like, okay, let's try a Bell state stabilization with just one more auxiliary level, which we are never going to use in our computational manifold, but we'll actually try to do a Bell state in a qubit system. So this is the minimal instance. And the idea is actually, again, the point is that we know from the reservoir engineering conditions that the total spin has to be conserved under the full Liouvillean dynamics in the computational manifold, which is where entangled state is supported. But what if I actually have an auxiliary channel and I break the symmetry in the higher space? And that's exactly what we do. We actually realize a protocol where you see there is no direct connection between where the entangled state lives, which is basically the 2 qubit 0-1 manifold. However, the qubit state actually is where the spin is not conserved. So there the symmetry is broken, and that gives a one-way channel to actually prepare my entanglement. So I'm actually forced to use this like kind of qubit dissipator in some sense. And the interesting thing is, just to confirm that it actually takes away this problem of trade-off, we actually find that as we increase the dissipation, both the error goes down and the rate increases, which is what you want. So just to show it more clearly, if I actually plot the steady state error and the time it takes to achieve that as a function of dissipation, as a parametric plot, as I increase my engineered dissipation, they both decrease. Whereas in the perturbative stabilization regime, they are anti-correlated. So it means that I can actually have non-perturbative driving in these kind of exact entanglement stabilization protocols, where actually it's not the error times the time which is constant, but it's actually the error over time which is actually the constant. So there is no actual fundamental bottleneck theoretically. And in fact, this is no longer a theorist proposal. Our experimental friends in circuit QED were able to do this. They used what are known as the parametric couplings, which are basically just pairwise interactions. So for people who do not know superconducting circuits, these are basically two transmon qubits. So the green and blue are basically superconducting atoms. This is a 3-level atom, this is a 2-level atom. You just choose to derive 3 levels instead of 2. And this is basically a simple harmonic oscillator, which is like a cavity with a dissipation on it. And using these kind of parametric interactions, which are basically just sinusoidally modulated couplings, they can actually choose the form of the interaction or the parity of the target state. So they can do either an odd or even parity entanglement. We can also institute tune the amplitude of the dissipation rate which we dial on the system. And interestingly, give in a fixed parity manifold using this phi sub p, you can also choose which target state, like whether it's a singlet or a triplet or any arbitrary odd parity state can be stabilized. In fact, they were able to do this experiment. These are tomographically reconstructed trajectories. They basically initialize their 2 qubits in any arbitrary state. Here, for clarity, they have initialized them in the joint ground state. They just turn on all the parametric interactions, and as the system stabilizes, it automatically settles into the desired target state with some fidelity. It looks very modest, this 84%, but if you look at their qubits, they were pretty crappy. Actually, they were 5 microseconds. So you see in fact, this experiment can run for like 50 microseconds and still the stabilization remains there, because that's the whole point of stabilized states. It's actually a unique attractor solution of your driven dissipative dynamics. And just to confirm the scaling which we predicted, they were able to actually measure these error as a function of increasing the drive strength, which actually increases the effective dissipation. And they were able to see this concurrent scaling, which essentially means it is really a non-perturbative stabilization. The theoretical bound is what is shown in the solid black line. They were slightly above it because there was a little bit of crosstalk. So people who work on these hardware platforms, they know how coherent leakage is a big problem. But in fact, it was weak enough that it did not change the scaling, at least the form of the scaling we predicted. It just made it a little steeper. And as I said, they can also do this kind of phase-based control of their target state. So this is actually a 2-qubit block sphere of odd parity. So the poles are product states. The equator is maximally entangled odd parity states, and somewhere on the sphere there's a non-maximally entangled pure state of odd parity. And you see, just by changing the phase of the drives, they were able to actually tune where they are on this block sphere on the equator without losing any purity or concurrence. So the purity and concurrence remains the same within the few percent while they are tuning their drives. So it's actually leads to, it can also lead to kind of a coherent control of the stabilized manifold without actually breaking the stabilization. So all this was very interesting, but it was actually proof of principle. So what the primary reason we were interested in quantum reservoir engineering was, this was the first bottleneck which turned out to be actually not so fundamental. But the question was, okay, this is actually nice from a point of view of 2-qubit demonstration, but is this really a scalable solution for doing some kind of long-range coherent stabilization? So for that, we actually looked around to see what is the meaning of scalable quantum reservoir engineering. And as it turns out, we were actually a bit surprised that unlike quantum circuit model or gate-based model, complexity in the domain of quantum reservoir engineering is very, very poorly understood. So in the complexity in the quantum circuit model is typically understood in terms of these kind of notions. For example, people talk about circuit depth, which is essentially some kind of the longest, the largest number of gates you can have between 2 qubits in a big quantum circuit, number of operations you can do per layer, which is circuit width. And then they say, okay, can I, given a n-qubit GHZ or an n-qubit W state, can I actually have reasonable complexity quantum circuits, which essentially means where my gates do not explode with the system size? Can I create a quantum state like an n-qubit GHZ with reasonable number of gates? And there actually exists quite a few variations of these things. So inspired by these ideas, we actually posed to ourselves, what should be a scalable reservoir engineering protocol? So again, number of gates is like a circuit depth. That in some sense translates into bounded depth interactions. What that means is that just because I'm stabilizing a large entangled state, I should not, my Hamiltonian interaction and my system-wide interaction should not scale in complexity with the complexity of the entangled state. If I have like 2-body interactions or 3-body interactions, those building blocks should be enough to construct the large entanglement stabilization. Similarly, in terms of circuit width or number of operations, that kind of boils down to low-degree polynomial scaling of resources, which essentially means that, okay, maybe I will need for 2 qubits just 2 or 3 terms in my Hamiltonian of low depth. But if I do a 10-qubit state stabilization, I should not need 100. So it basically means that the required drive strengths and the decay rates and their number should not grow too size. And then the final idea is to actually stay true to this no intrinsic error, that the ideal steady state should exactly be my target state, because in fact it has been known that these intrinsic errors themselves can scale poorly with n, which essentially means that if a protocol which is perturbative works very well for 2 or 3 qubits, may not work at all for 20 qubits, just because the intrinsic error itself has a system size dependence. So the best bet is to just get rid of it entirely, and that's what we are going to do. So the choice of the target state which we did for this was this W state, which is a specific class of decay states. It's actually a permutation symmetric combination of a fixed number of excitations in n qubits. We are going to particularly use k is equal to 1, so 1 excitation distributed in n qubits. There's a lot of appeal for quantum reservoir engineering for these kind of states. First of all, that you can see that the distance between the code words or the component wave functions which form this state does not grow with system size. See, if there's 1 excitation, all component wave functions have 1 excitation. It's just which qubit has it changes. Whereas in the G at Z, you know that as you scale the system size, you also scale the number of excitation because it's 0 tensored n plus 1 tensored n. So in that sense, GHZ already looks like a no-go for actually trying to do this kind of stabilization with bounded depth interactions. And the second very interesting point about W states is that as you increase the system size, which means that if you have an n qubit W, where each qubit has a local decay and decoherence rate. Here's what I'm plotting, the decay rate of the n qubit W state under the action of all these independently local decay channels. For the final decay rate actually looks something like this. So for n goes to infinity, it actually remains bounded. You see, because it's just gamma minus plus 4 gamma z, where gamma z is the dephase, local dephasing, and gamma minus local relaxation. And as I already told you earlier, a few slides earlier, that to be in the reservoir engineering regime, we actually need this decay rate to be strictly smaller than the engineered dissipation rate. So this becomes a losing battle if your decoherence rate themselves scale with system size, and that's what happens with GHZ. So from both these points, W state sounds like a great choice. And in fact, only a month ago, there was actually a very interesting result coming from the Caltech group, where they showed that how W state cannot be actually the sole ground state of a gapped Hamiltonian. So it means that adiabatic preparation of these states, using just Hamiltonians, is anyways very, very hard. In fact, it's impossible according to this no-go theorem. So interestingly, let's see if dissipation allows us to do this. So we actually first looked at the traditional approach to reservoir engineering, where this was actually something which was also touched upon in the last talk, where you basically have some kind of a common motional mode, like in a trapped ion setting, and you have multiple, atoms or ions in the talking to that common motional mode. So basically, if you think of that mode as some kind of a dissipative bosonic mode, there are all these qubits talking to it, and you trace out this bosonic, this degree of freedom, which is actually which is your engineered bar. That leads to an engineered dissipator of this form, which I already showed is kind of a quasi-linear, quasi-local dissipator. And you can say, okay, I want the W state to basically be the null state of this dissipator. Just very simple algebra shows you, okay, yeah, that's possible. So all looks good. And interestingly, these kind of dissipation engineering protocols is what I will call the long-range dissipation. Because here, the width of the dissipation, just like the circuit width was the number of operations which happen in parallel. So the dissipator mode in parallel talks to the full system. So which essentially means that the dissipation width scales with system size, and this is a naturally long range interactions. And plus it requires only one mode. So the number of dissipators is constant. So what we did was instead to take a modular approach to reservoir engineering, where we said, okay, what if we actually make the dissipation width constant and make the number of dissipators scale with system size? So let me try to explain this a bit. So imagine that instead of 5 qubits all coupled to the same mode, I actually make this kind of a dissipation engineering arrangement where I have 3 qubits coupled to some kind of a dissipative bosonic mode, and the third qubit shared with the second mode, and the third, fourth, and fifth qubits are talking to the second bosonic mode. So I would call this as a width 3 dissipator because it is talking to 3 qubits at a time. The total system size is 5. And this is the kind of sum of 2 dissipators I will get because these 2 bosonic modes are completely independent. You can do some interesting games if they are correlated, but for the purposes of this talk, I'm going to consider them completely uncorrelated. So basically what it will do, it basically means that you can actually check based on the previous slide that the first dissipator, which will actually stabilize a W state on the first 3 qubits, plus also a ground state on the first 3 qubits because these are just annihilation operators, right? So the ground state is also a dark state. And similarly, the second dissipator will stabilize a W state on the remaining 3, 4, 5 qubits and a ground state also on that joint, on these qubits. So basically, each dissipator supports both W sub k and 0 tensor k as their dark states on the subsets of these qubits. So the idea is actually the following, that if you actually purify smaller subsystems using modular dissipation of constant width and then make them intersect using these stitching qubits, basically you will get a W the n qubit W state and the joint ground state as the overall null states of the full system. And that's because the W state of the first 3 qubits is not in the null state of the third 3, 4, 5 qubits. So when you actually take this kind of a Venn diagram approach to dissipation engineering, the intersection of the various kernels just means the null space of the dissipators, it only selects the joint W state and the joint ground state as the overall null states. And then the Hamiltonian, which is the, again, remember it was the h psi equal to the lambda psi. So the Hamiltonian has only one role to play. It has to give me a deterministic feedback such that it excites the joint ground state but not the W state. So then I'm done, because dissipator selects just these 2 states. Hamiltonian does not prefer the joint ground state. So the n qubit W state is the only joint entangled state which will appear of your driven dissipator dynamics. And in fact, these kind of ideas have recently been also explored for these AKLT states, which are known to have a topological order in their ground state, using modular measurements, just like what I'm using as modular dissipation. They use modular measurement schemes, but they have to use post-selection, so it has some qubit overhead. And there have been some really interesting recent works on how maybe even thermodynamics of extractable work from these systems can actually be better if you do not demand all-to-all connectivity in qubit systems. So just to take this idea forward, so this is our kind of a shorthand for understanding what this kind of dissipator graphs looks like. So each dissipator can be thought of as a hyper edge, which connects 3 vertices. And basically, if I extend this idea to several qubits, these are the minimal dissipator graphs which we come up with from n equal to 3 to n equal to 9, which I am showing you, using hyper edges of width 3. And when we actually look at the performance of these schemes, this is, so again, we compare ourselves to the traditional approach, which is where you couple all the qubits to the same mode. We actually find that the time to stabilization actually scales exponentially, irrespective of what kind of Hamiltonian games you play. You can also play this game with Hamiltonian using maximal versus minimum terms, which I'm not going to discuss in detail for the interest of time. Whereas when we actually try to do this modular dissipation, we actually see a polynomial scaling. So we actually find an exponential advantage when you do not demand an all-to-all connectivity in dissipator hypergraphs, which is actually kind of antithetical to the idea of how all-to-all connectivity is actually a desirable feature in Hamiltonian physics. And in fact, we actually did this particular idea that, okay, we are also increasing the number of dissipators with the system size. So is the advantage just trivial because the dissipation number of dissipation channels is increasing? And the answer is actually no, it's actually more complicated than that. Here I'm plotting stabilization rate as a function of number of dissipators for a fixed number of qubits and a fixed dissipation width. So again, you have 5 qubits and you are making hyper edges of width 3. So if you can have 5 choose 3, which means the maximum number of edges you can have is 10. So the minimum you can go from anywhere between 2 to 10, and there is actually a freak case that even one single edge works, but that is actually an end coupled thing, so it's very complicated. So, but these are the distributions which are actually obtained by actually randomizing the dissipator parameters. The interesting thing is, so there's a lot of information on this plot, but the 2 most important things are that even for randomized dissipator parameters, the scheme keeps working, which essentially means that there's a lot of robustness in these protocols to disorder. And then the black dots are basically the median performance. And as you can see, if it was just a trivial change or improvement because of increase in the number of dissipation channels, they should have followed a linear trend, but actually it doesn't. So it's not just a monotonic increase with the more the dissipation, the faster the rate. It actually is some kind of a cooperative shielding effect, which actually happens in these systems with short-range dissipation. And just to confirm that the modular reservoir protocols really, this system has no intrinsic error. We actually study the steady state error as a function of system size from 3 to 8 for several dissipative maps. So it becomes a little hard to do it for more than 10. And you see that it seems like that it's slightly increasing with system size. This is some kind of an entanglement witness, the hatched region. So I'm using the different colors show different decoherence rates, different local decoherence. So you can see that if the local decoherence is very large, of course, for large system sizes, you cannot actually witness this entanglement efficiently. But still, for low or reasonable orders of dissipation, you can actually find that this entanglement witness is certified. So this is really certifiable. Another thing is that if I actually can rescale this steady state error with the local dissipation, I just get an almost constant value of 1, which essentially again proves that there is no intrinsic error. The entire steady state error was coming because of local decoherence, which was essentially the point of exact schemes, that there should be no error which is intrinsic to the scheme. The entire error is just because of the decoherence or the hardware platform. So that is why this is almost flat. If there was any intrinsic error, it would actually have scaled linearly, which is the signature of a perturbative scheme, not an exact scheme. So with this, I will actually just end. I think I'm almost at the end of my time. That I hope I have given you a taste of why it is worth pursuing engineered dissipation as a resource, especially for stabilizing quantum coherences in large quantum systems. And intrinsically, we find these examples in quantum reservoir engineering where long-range interactions can actually be a liability. And sometimes short-range interactions can give you exponential advantages besides being practically more friendly. So thanks again, and I'll take questions.
Thank you, Archana, for the nice talk. Questions?
Thank you so much, Archana. Can you go back to the discussion of these dark states and you had at the very earlier part of your talk? There was like you had a system.
Let me go there.
Can you help me understand the intuition behind how you define? One more. Yeah, exactly.
Yeah.
So can you help me understand why the intuition behind what you mean by this unique dark state? Is the dark state somehow in the phi 0 state, or it's in the psi? And
no, the psi. So psi is my dark state, the desired dark state, and
okay.
It's unique if it's the only state which satisfies both these conditions. These conditions, this H is basically the system Hamiltonian, or the drive Hamiltonian, and C is the jump operator which you have engineered. So if you can actually have more than one dark states, more than one state which satisfy these conditions, and then actually it can be a trouble if it is accidental, because then what happens is, it's kind of the problem of degeneracy in open systems. You see, in Hamiltonian systems, if you have a degeneracy, what do? You actually find a superposition of those states is also a valid eigenstate. But in open systems, if you have multiple pure states, which are not carefully engineered and they simultaneously satisfy these conditions, you get a mixture of those pure states. And that means that the overall state is mixed, not pure.
And if you have like a quasi-degenerate grouping of subradiant states, like in a many-body subradiant context, can you still engineer them, or do you lose that pure state that you wanted at the beginning?
So that's what I'm saying. If you engineer it carefully, there is this concept of decoherence-free subspace, which is a DFS, where the idea is that you can actually engineer a subspace of dark states, which actually talk to each other through a Hamiltonian. The problem is that as soon as you have multiple states or steady states of the system, the problem becomes initial state dependent. So depending on where you initialize the system depends on which target state you get into.
Thank you.
Please.
Yeah, thank you for the nice talk. So from the same slide, so you talk about this, scaling with the W state, but for the GHZ state, we actually know that if you want the GHZ state to be a eigenstate of a non-degenerate Hamiltonian, you actually would need like k-body interactions, like the interaction body has to scale with the system size. So does that mean that effectively you don't have an efficient protocol to prepare the GHZ state, even with this reservoir computing, engineering?
Excellent question. Yes. So GHZ is there's a caveat here. So if you demand a GHZ state, then you actually know that to stabilize a GHZ state, you need an n-body operator to stabilize it. However, if you just want to say, I want to have an arbitrary superposition of GHZ plus and minus states, that's actually easier to do. Because that can be just done with nearest ZZ operators. So it actually, so in some sense, sometimes reservoir engineering a pure unique state is harder than reservoir engineering a subspace. Because you're not trying to introduce, you're trying to just do a parity selection, not a phase selection, if that makes sense.
More questions? Perhaps a curiosity on the experimental implementation of this.
Sure. Yeah. This one?
I guess this was just any sort of initial
Okay,
idea. I wanted to understand a little bit better regarding the second part of the presentation.
We are always thinking about what can be experimentally implemented. In fact, that is the reason that we actually stick to bounded depth interaction. So bounded depth essentially means that, see, the interaction is always pairwise or at most like maybe 3 body terms, but not more than that, because that becomes experimentally challenging to do. So whatever protocols I showed, including for the modular dissipation, they actually have dissipative interactions which are of this type. And then I think I might actually, I'm not sure if I can. I don't want to spread, like, I have to go through all the slides, unfortunately. There is actually the Hamiltonian, which actually looks like these. It's actually the simpler, it's a combination of single qubit drives and just these 3 body terms. And we proved in this paper that it's actually insufficient for doing any n-body W-type entanglement. So that's what I meant by bounded depth interactions, that irrespective of how big a state you are generating, the complexity of the building blocks in your Hamiltonian should not scale in complexity in terms of the number of operators you have to multiply.
Okay. Niccolo, you have a question?
Yeah, actually,
Sure.
So let me move in the audience. Can you go back?
I have to go back.
Sorry.
Okay. That's okay. That's all right.
No, it's actually at the beginning. So
At the beginning.
when you were talking about the fidelity of 84%.
Yes.
So I wanted to understand. So you say this is related to the fact that you have that the qubit is not
very good.
Exactly.
Actually.
But can you correct?
Yes.
So
very good question. Yes. So we actually there were actually a lot of problems in their chip. It was actually a pandemic era chip, so they were kind of stuck with it. They couldn't make a new sample. But the point is that, like, for example, they had it's actually very low. Like, I think it's actually a bit embarrassingly low for superconducting qubit technology, these kind of coherence times. We actually estimated that if they were just like 10 microseconds, this number would have all been 92. And when if they were able to use their blue sideband or slightly larger Gs, they were limited by the kind of effective GP they could get, the effective coupling. I think it was like it was like 3 or 4 megahertz. If it was and the optimal is like 3/2 of kappa. So if they were around 8, that would be like 98.
Okay.
So it was actually, we did some kind of an error budgeting. So part of the problem was just low qubit coherence, and part of it was that they were not optimal in terms of the what optimal G they want.
Okay. And maybe another, an explanation about you had some violin plot.
The violin plot.
Yeah, I always have difficulty understanding those. So.
Yes. Sorry, let me go there. Yeah, this one.
So basically, this gives me the distribution of the stabilization when you vary at random the BAT parameters.
The dissipative parameters.
Yes.
Yes.
So, but I understand, what are the points?
So, okay, so this is entirely the distribution. We have just put they actually, okay, so let me say this. So the colors are the distribution. So the distribution is like this.
Yeah.
Different colors tell you the number of dissipators, which are equivalent ways of connect. For example, green is equivalent way of connecting 3 dissipators on a map of 5 vertices.
So, so the empty points, what's the meaning of
these points? You mean?
Not the empty one, the circle, this one.
Oh no, okay, they just appear empty. There's just a long tail. We are just making a kind of a.
Okay.
So that is what happens because you have so many parameters now to tune. This is just a long tail of the distribution.
Yeah. Sorry, I always get confused. Thank you very much.
These are not very Gaussian distributions, as you can see from the long tails which you did. Yeah.
Another question here.
Can you go to the graph networks you had? Is there a
Yes.
reason why n equals 8 has more configurations than 9?
Very good point. So that is because you see, in fact, okay, let's put it this way. If you look at it closely, the number of dissipator or hyper edges you need remains the same for n plus 1 odd qubits between and n even qubits. Like if I see for 4, you have to share an edge, you still need 2 dissipators, and for 5, you still need 2 dissipators. Similarly, 6 and 7, they both need 3. So 6 is a bit more complicated because you have to share an edge. So if you look at it carefully, you get these kind of pinwheel diagrams, and I didn't comment on it. These turn out to be actually most efficient, even within these 4. Whereas the most inefficient ones are these rings, which you always get in the even, because you have to share an edge. So if, let's put it this way, if my dissipation width was 4, then the thing would be different. It's like 4, n mod 4, which will have the repetition in some sense. So this is,
Thank you.
does that make sense?
Yes.
Hi. So just to clarify, so each one of these dissipative channels, does that represent like some kind of jump operator in your master equation? Yes. So you're saying that having a very non-local dissipation operator is less efficient than having these kind of short range? Okay.
Yes.
Okay, cool.
Any final question? Okay, if not, let's thank Archana again. And of course, all the speakers of the morning session. Now we're headed to our lunch, and we reconvene at 2 p.m.